Welcome all. In this session, we'll be looking at the metabolism of methionine. Methionine is a very important amino acid in the body. So methionine is one of the 4 amino acids that usually form succinyl-CoA. Remember the other 3 include valine, isoleucine, and threonine. So those 4 will form succinyl-CoA. So methionine is a glucogenic amino acid. So this sulfur-containing amino acid, as I've said, deserves special attention because it is converted to S-adenosyl methionine, abbreviated as SAM, and others also call it adoMet. Adenosyl methionine can also be known as adoMet, since it is a major methyl group donor in one carbon metabolism. It usually donates methyl groups. So let's say you want to form epinephrine from norepinephrine. You simply methylate norepinephrine. You add a methyl group to the, say, norepinephrine. You'll get epinephrine. Or you want to form choline from ethanolamine. You add 3 methyl groups. These methyl groups are brought by the SAM, S-adenosyl methionine. So it is also the source of homocysteine. Homocysteine is used in the biosynthesis of cysteine, and and also it is associated with the atherosclerotic vascular diseases and thrombosis. Maybe we'll see that. So for now, let's start at this. So this is the metabolism of methionine. Here, you start with methionine. You start with methionine. You want to form, you want to obtain S-adenosyl methionine from methionine. So you simply add an adenosyl group. So this is your methionine here. So you add in ATP. Remember, ATP will come with an adenosyl group and three phosphates. So you simply remove the 3 phosphates and add the adenosyl group into to the methionine. So this is the structure of methionine. Let me excluding the adenosine. So this is the structure of methionine. This is the one I'm trying to, that is methionine. So you can see this is your alpha carbon here, where you have your carbonyl carbon, amide group, and so this adenosine group is added to this adenosine group here. You can see it is added to the sulfur here. Okay, so then the reaction is catalyzed by this enzyme, methionine adenosyl transferase. You see, we will remove the 3 ATPs. We will remove one in form of an organic phosphate and a pyrophosphate. This pyrophosphate is immediately cleaved into 2 inorganic phosphates. We will add water here. So you will add water to the, here you will add water, and you will get your 2 phosphates, inorganic phosphates. This reaction is catalyzed by the enzyme pyrophosphorylase. Pyrophosphorylase. So the pyrophosphorilase enzyme is the one which catalyzes that reaction here. You add water here to get to the pyrophosphate to get 2 inorganic phosphates. So after forming the, after adding the adenosine group to methionine, you get your S-adenosyl methionine as you wanted. So, sorry for that. So after forming your S-adenosyl methionine, this is the one which will go to catalyze methylation reaction, where we will be adding methyl groups to methyl acceptor. So you can see here, you bringing a methyl acceptor. Methyl acceptor can be anything that just wants to be methylated. So after adding this methyl group, the methyl group added is this one. So after adding it, the S-adenosyl methionine will undergo demethylation, removal of the methyl group. So after removing the methyl group, you are left with this new compound here. So you can see the methyl group that was there has been taken away by the methyl acceptor. So this methyl acceptor can be, let's say, norepinephrine, your noradrenaline. After methylating norepinephrine, it will become epinephrine, your adrenaline. You can also methylate other products such as ethanoramine to form choline, and many other examples. Even you can methylate RNA to form methylated RNA. So this new compound formed is now known as the S-adenosyl homocysteine. So if you remove this adenosine group, this is homocysteine. See, its structure is like homologous to that of cysteine. Only this, it has only an addition, only the methylene. It has an addition methylene group. Were it not for that methylene, it would be cysteine. So it is somewhat homologous to cysteine. So it is homocysteine. So after forming the homocysteine, what next? That reaction is catalyzed, as you know, by a methyl transferase. It simply transfers the methyl group. Now the S-adenosyl homocysteine undergoes, we will cleave a bond here. We cleave a bond. Which bond will we cleave? I'm sure you can see it. We will cleave this bond to release adenosine. Okay, we add water, we cleave that bond, we release the adenosine, and we are left with the homocysteine. Okay, now that reaction is catalyzed by S-adenosyl homocysteine hydrolase. We are adding water. Other texts can call it the S-adenosyl homocysteinase. So, but I like to call it a hydrolase so that I can know what is happening. We are cleaving a bond using water. So this adenosine might go to form ATP. Okay. So after forming now homocysteine, now we have formed homocysteine after the removal of the adenosine group. What next? What next? It will depend on the state of your body. If you have deficiency of methionine, we will take this pathway. If you have deficiency of methionine in your body, we will take this pathway. If you have adequate methionine, so there is no need to form any other methionine, you will take this pathway. So this is methionine deficiency. You don't have methionine in your body. This there is adequate. So let's start with this one for the formation of methionine. You simply need to add a methyl group to homocysteine. When you simply add a methyl group to homocysteine, you will form your methionine. Okay, it is that simple. So what contributes? So when you add a methyl group to this homocysteine, you will get your methionine, as you can see here. Now, who is the donor? Who is the donor of this methyl group? The donor of this methyl group is this compound here, a very important compound, N5-methyl tetrahydrofolate. Okay, so it is a tetrahydrofolate which is methylated at the nitrogen at position number 5. The tetrahydrofolate is a derivative of folic acid. Folic acid is your vitamin B9. Okay, so it is the one which brings the methyl group. A reaction catalyzed by methionine synthase, not a synthetase, synthase. In this reaction, you need methylcobalamin. Methylcobalamin. Remember, it's B12. So those two are very important information of methionine. After demethylation of the methyl tetrahydrofolate, you will get your tetrahydrofolate, which can go and pick another methyl group. That is when you have methionine deficiency. What if you have enough methionine? I said you will take this pathway. So what happens in that pathway? You already have enough methionine. So homocysteine, we will take homocysteine, the one which we formed from S-adenoside homocysteine via the S-adenoside homocysteine hydrolase reaction. We take that homocysteine, we add serine to it. Serine is also an amino acid. Now, this reaction requires vitamin B6, your pyridoxal phosphate, and the reaction which is catalyzed by cystathione beta synthase. So, after adding homocysteine and serine, you get your cystathione here. Now, cystathione is cleaved by cystathionase. We cleave, where do we cleave? We will cleave at this position here. Maybe I should use a different color there. So we cleave at this position of cystathione. We simply add water. The enzyme is cystathionase. Also, this reaction will require B6, your pyridoxal phosphate. So after forming after cleaving there, this group which is on your right, let's see, after this on your right, maybe I should point it or something. Now this one, this group there is the one which will give you your cysteine. Remember, there is cysteine. Then this other one which has remained is your alpha ketobutyrate, and you also release ammonia. Alpha ketobutyrate will go and form your propionyl-CoA. Propionyl-CoA will be converted to succinyl-CoA first, but it will first pass through methyl-malonyl. So that is the metabolism of homocysteine. Now, allow me to show you something which I find important. So, I don't know if you will allow me, but you can allow me. I don't know. So, I wanted to show you something about you should remember those I've said about the, let me show you something about, the how some disease processes that affect this methionine metabolism, because it is affected by some diseases which are of great importance to us. Maybe it's here. Yes. Okay. Sorry for that, by the way. Here we are. Yes. Now, we are here methionine. So here, as I had said, remember methionine. So here we have your methionine. It is converted to S-adenosyl methionine, your SAM or adoMet. Here we have the methionine adenosyl transferase. Then it is demethylated to form S-adenosyl homocysteine, a methyl transferase there. Then we have the S-adenosyl homocysteine hydrolase. We cleave to form, we cleave the adenosyl group, we remove the adenosyl group to be left with homocysteine. Now, the reaction of homocysteine to cystathione, where we added serine, the cystathione, the beta cystathione synthase reaction, if you have deficiency of that enzyme, you will have homocysteinuria. Accumulation, so you will not be metabolizing homocysteine, so it will accumulate. That is homocysteinuria. So it usually accumulates in the urine. Also, methionine homocysteine will also elevate, but you have very low cysteine because you are not synthesizing it. Its clinical presentation are skeletal abnormalities, increased risk of clotting, you have thrombosis, lens dislocation, and intellectual disability. So, cystathione, I said cystathione via the enzyme cystathionase, we cleave to form cysteine and alpha ketobutyrate. Now, if you have deficiency of that enzyme, you will have cystathionuria, accumulation of cystathione. So there will be also deficiency of cysteine. So remember, as I've said, alpha ketobutyrate is converted to propionyl-CoA. Propionyl-CoA is the one which is now converted to succinyl-CoA, but will first pass through methyl-malonyl. Remember, from propionyl-CoA, we first form D-methyl-malonyl, reaction catalyzed by propionyl-CoA carboxylase, biotin requiring reaction. Then D-methyl-malonyl is converted to L-methyl-malonyl, reaction catalyzed by the racemase. Then L-methyl-malonyl is converted to succinyl-CoA by a mutase, a reaction which usually require the mutase. Yeah. So if you have deficiency of that mutase, methyl-malonyl-CoA mutase, you'll have methylmalonic acidemia. Methylmalonyl will accumulate in your body and it is an acid. So it can be caused by either deficiency of that disease of the enzyme. You don't have the methylmalonyl-CoA mutase, or you don't have its coenzyme, the adenosyl cobalamin, you don't have it. Or not necessarily don't have it, your body is not being able to absorb B12. Maybe your gastric mucosa is not producing the intrinsic factor, so you are not being able to absorb. So thank you for your time, and yeah, that was the metabolism of methionine, so, and some diseases that affect that pathway. Thank you, and subscribe for more.